chances are that you've noticed that different kinds of liquids have different properties, physical properties. And water is particularly unique. You may have noticed how it beads up, for example, when you put it on a piece of wax paper. Actually, water has such remarkable properties that if it was relatively rare on Earth, it would be considered a very exotic substance. I would like to think that somewhere in the universe there's a community of civilizations from different planets. And if there was such a community, the chances are pretty good that planets with the quantity of water that we experience on Earth would be kind of rare. Earth is, in fact, known as the water planet. It's the only one in the solar system with a known significant amount of water, and the surface is covered with 70% of it. So we think of water as an everyday substance, but it is really quite remarkable. Now, what you can do as a little experiment, and you may have done this before, is to take a little piece of wax paper and take a drop of water and plop it on the top and notice its properties. You can do little things like see how high you can pile the water drops, see how far it can spread out before it finally collapses, and maybe see how many drops you can add and stay inside a little dime-sized circle, little activities like that. And compare it maybe with another substance. I kind of compared it with alcohol, which is a different liquid. It smells different, but other than that, it doesn't look remarkably different from water. And if you compare the surface tension properties of water with that of something like alcohol or oil or something that's not aqueous, you can see one very remarkable difference, and that is that water tends to have a property that we call cohesion. It tends to stick together. It's a sticky substance. So if we look at the structure of water molecules, maybe we can try to explain this cohesive property. I heard somebody mention hydrogen bonding, so perhaps you've had a little bit of this sort of thing. But I'm going to go backtrack a little bit to the basic structure of atoms and then work my way into the structure of water molecules and eventually how water molecules fit into the structure of cells. Water molecules, as I mentioned, tend to stick to each other. They consist of hydrogen and oxygen, 2 atoms of hydrogen, 1 atom of oxygen per molecule. Hydrogen atoms, as you know, consist of a nucleus, as do all atoms, and an electron shell, or electrons orbiting. Hydrogen is the most common element in the universe. It consists of a single proton in the nucleus and a single electron that orbits the nucleus, forming what we call a shell. Oxygen atoms have 8 protons and 8 electrons. Hydrogen atoms have 1 proton and 1 electron. Oxygen atoms have 8 protons, 8 electrons. They're much bigger. But we don't find hydrogen atoms normally laying around in the air and so on. Same thing with oxygen. They are seldom found as single atoms, as a matter of fact. That's what I was going to explain. Hydrogen and oxygen gases are actually diatomic. Hydrogen is H2, oxygen is O2, as we know. And I drew a hydrogen molecule here because to draw an oxygen molecule was just too darn difficult. The electron shell is there's more than 1 electron shell around an oxygen molecule, which explains something that I'm going to talk about in a little bit. But both elements are gases at room temperature and pressure. Both of them have a shared electron shell surrounding 2 nuclei. One of the properties that we know of a gas is that it can fill any space, any vacuum. And it'll expand to fill whatever volume of space you happen to put it into and be distributed uniformly. That's a good question is, why do they do that? Why would the gases expand? What makes material or matter a gas in the first place? Why does it expand to fill any possible vacuum? And that leads us to Avogadro's principle. Avogadro is known for Avogadro's number, of course. Right, the number of atoms in a mole, or I should say the quantity of a mole, because you could talk about moles of atoms, you can talk about moles of molecules. Is no reason that number which describes a very, very large amount of things conveniently, can't be used to describe the numbers of stars in the universe or the number of grains of sand in the ocean for that matter. Right? The mole is simply a way of expressing a large number. But anyway, Avogadro never calculated his own number. It was named after, actually in his honor, I believe. He is known for a suggestion that he made back in 1811, which is called Avogadro's principle. And Avogadro's principle holds that if you have equal volumes of gases and they are at equal temperature and at the same pressure, they contain an equal number of molecules. You're thinking, so what? What's this got to do with water? Well, in 1811, modern atomic theory hadn't been developed yet. Wasn't quite certain what molecules were or if even molecules existed. John Dalton suggested at that time that all matter consisted of single atoms. And when atoms were combined, that's how chemical reactions took place. Avogadro was the first to suggest the presence or the existence of molecules, where more than one atom of one type could be mixed with an atom of another. Eventually, experiments were done with gases, where it was discovered that it might take 2 volumes of one gas under constant conditions and just 1 volume of another gas to make a compound such as water. It takes 1 volume of oxygen, 2 volumes of hydrogen to make 1 quantity of water without any gas left over. So mixing gases in chemical reactions required integral numbers in terms of the volumes of gases. But back to the, and that eventually led to this concept of atoms being combined to make molecules and so on. But back to the original concept here, why do molecules in gases spread out to fill any kind of a vacuum? Well, in order for that to happen, the molecules, one model anyway, is that the molecules repel each other. They get close to each other to coalesce to form, let's say, a solid state. They can't. They get so close and they're repelled. And if they repel each other, then they're going to be distributed fairly uniformly, all things being equal, and we have a gas. And if you expand the volume, well, a repulsive force might diminish with the space between 2 atoms, let's say, but they're nevertheless going to fill to fill the whole volume. Well, that makes a lot of sense. Eventually, the experiments were done to demonstrate that. It took a long time after the development of atomic theory to really develop the concept. But I want to go back to what kind of forces might be involved here. We have to think about what would make 2 objects repel each other. And let's see. Well, there are 4 fundamental forces in nature that we know about. And 2 of them are the strong and weak forces, which are involved in holding atoms together and the particles of atoms. That's not us. Okay, we're not working at that level. Gravity is a 3rd force that we have identified in physics, but gravity is an extremely weak force. It requires great big objects. We're stuck to the Earth because the Earth is so doggone big. Now, if you were to try to do an experiment to demonstrate gravity between 2 smaller objects, let's say a ping pong ball and a bowling ball. Okay, the bowling ball should attract the ping pong ball. Well, you can put them in a bell jar and you can hang them from threads. The bowling ball thread have to be pretty heavy, I think, and try to demonstrate gravity, but you couldn't control the experiment because it would say the force of gravity is so weak that any vibration in the room, any walking across the floor, any air currents, changes in temperature from one side of the bell jar to the other, even the slightest change, and you'd cause disturbances that would be far greater. They'd cause far greater movement than anything you could detect is due to gravity. So whatever is causing our molecules to repel each other is probably not gravity. It's too weak a force. So that leaves only one, and that's electromagnetic force. And it's a very relevant force. Everything, friction and chemical reactions, why things stick together, why cars move, all the forces, physical forces that we see and measure in everyday life are due to electromagnetic interactions, remarkable as it might seem.
I have a question.
Uh-huh.
The molecules in a gas, do they bump into each other, or just they never bump into each other just because
They can't, and I'm going to explain that in a minute.
My students asked me that yesterday.
All right. Well, that's cool. Well, you know, you can give them a very nice demonstration, too, and that was just a perfect question because I'm going to do that right now. I have a little demonstration here. I hope this works. It has to be really dry to do this. Okay. Oh, I need a volunteer. Can you come up, please? This is important. I need help. Everybody knows I need help. All right. There we go. Okay, I just need to hold your hands out like this. And this way. Oh, that's good. Okay. This way. If you face me. There we go. Perfect. Okay. Sorry. All right. Would you hold the roll with your left hand? Is that your left hand? Mm-hmm. Okay. I can't tell. I'm Les Dixon. Okay. Oh, and I need to stick this on here. There we go. Don't touch the rest of the tape, please. Okay. Here we go. Okay, here we are. Okay, cool. May I have it? Okay, thank you. I'll need you one more time. No, I'm good. Thank you. You can set the tape. All right, cool. Okay, so I just peeled off 2 pieces of electrical tape, and this is why I was kind of hoping it's nice and dry in here, because I'm going to try to bring them together and touch the ends. And let's see if I can bring them together and touch the ends. Will they? Okay. I'm not cheating, honest. There, caught the... All right. Wow, look at that. Oh, would you? Okay, you can't. There's something about this electrical... See, the tops, I brought the tops together. The ends will not come together. Yeah, that was the adhesive side. Okay, let's try it the other way. Nope, it's just not going to work. Okay? In a real dry room, if this was up north and it was real dry, one of those days where you walk up to the doorknob and try to touch it and it snaps... These things would be way apart. Really cool. Okay, so this is the adhesive side here, and this is the dry side here. I'm going to try to put them together, force them together, and I want to try something else here. Oops, wrong side. Okay. I'll get it. You don't want to touch the tape too much when you do this. Okay. I'm going to make sure they're really attached here. Just kind of rub that. Yeah. I don't want to use my hands because my fingers are moist, and moisture will drain the electrons and kind of redistribute everything, and this thing doesn't work. And would you look at that? Okay, I should have made a couple of tabs here too. If you do this demonstration, take the first inch or so of tape and make a tab so you can get the stuff apart. There we go. Oh, geez. All right. There. All right. And then you want to kind of just rip them apart. Okay, cool. We'll just not worry about that little loop there. What happens now? Let's see. Whoops. Wow. That was cool. They come right together, don't they? Okay. I'm going to explain that a little bit later. You notice that when I brought the 2 close together, that I got pretty close before they suddenly accelerated toward each other and snapped, right? And I didn't fake that, honest. You can try it for yourself. Oh, that was wonderful. So, I'm going to explain this in a little bit, but the lesson here is that this is obviously a demonstration of electrostatic or electromagnetic force. Attraction in this case, and in the first case it was a repulsion. And it kind of shows you how perhaps that molecules might be able to attract or repel each other as well. Gas molecules repel each other not because they have a net charge on them. They're all neutral. Hydrogen gas, oxygen gas have the same number of positive charges in the nucleus as they do electrons, or charged due to electrons orbiting the nuclei. They're neutral molecules, but as the molecules become closer and closer together, the electron shells come together, and of course, when electrons orbit the nucleus, they form what we call a shell. You don't know where that electron is going to be at any given time, but we do know it occupies a very discrete space around the nuclei. And that space we call a shell. You bring two shells together. The closer you get, the more those shells repel each other. And so as the gas molecules are bouncing around, because there is temperature in this room, temperature, in fact, is defined as molecular motion. If we were at absolute zero, nothing would be moving. Not even the molecules would be vibrating. Because the room has temperature, the gas molecules here are bouncing around, and every time a couple of molecules get closer together, the closer they get, the greater the repulsive force, and they're driven back apart again. So what we have then is the reason for gases spreading to fill a vacuum is in fact electrostatic or electromagnetic repulsion. All right, well that's kind of cool, but you're probably interested in why water is cohesive. And so somewhere I've got to get around to talking about how molecules can attract each other, not why they repel each other. So I'm going to digress a little more, though, and talk about ionic bonds. And then we'll get to it. This is a neat little digression that I just had to do. If you're familiar with the metal sodium, probably not personally, but you've heard that you don't mess around with sodium metal. We have to store it in oil, because if it's exposed to moisture or dropped in a toilet, which somebody will do, they'll sneak out of chemistry lab, drop it in the fixture, boom, everybody gets all excited. I've seen it happen. It's not pretty. But anyway, sodium interacts with water and in a very violent way. You can also so it's a very reactive compound. Chlorine gas, we know, is rather nasty stuff, too. I mean, it's vicious, horrible, poisonous. You don't want to get anywhere near this stuff. You take, if you mix, is it bleach and ammonia? Is that it? You don't want to do that at home. Watch your cleaning agents, because when you can release chlorine gas, it's not pretty. But if we take metallic sodium and we take chlorine gas and we dress ourselves up in safety gear and so on, and we shove this stuff under a hood way back and pray that we don't blow the building up, we will bring them together. We will have a violent reaction. I mean, just a huge energy release, kaboom. And in the end, what we'll wind up with is table salt. Perfectly, and you can just scoop some up and lick it, put it on your hamburger buns, whatever it is. It's perfectly, as long as there's no chlorine or sodium left over anyway. Sodium chloride. And the sodium atoms, which are now no longer hooked to each other, but they are in fact positively charged, are now hooked to chlorine atoms, which are no longer in the form of a gas, but they've reacted with the sodium, and so NaCl consists of a positive sodium ion, a negatively charged chloride ion, and they're stuck together. Now, I brought this up about sodium chloride because I think we've seen with the tape demonstration that electrostatic forces or electromagnetic forces are pretty powerful. I mean, tape is relative to those little tiny charged particles. Relative to an electron, a piece of tape is huge. And there isn't that much of a charge difference with the tape. There aren't that many electrons in excess on one side or the other. I'll bring that up in a minute. But it was enough of an energy difference that when we brought the tape together, the mass of that tape was accelerated together and touched or forced apart. So ionic bonds or electromagnetic repulsion, attraction, those forces are pretty powerful. And yet, if we take sodium chloride, which is stuck together, a positive ion and a negative ion stuck together, we throw it in water, it disperses. The bonds come apart, and we have sodium ions that are evenly dispersed in the water, and we have chloride ions that are evenly dispersed in the water. Why? This is bizarre. There's something about water that allows that to happen, and it can't be a direct electromagnetic force that's causing it, can it? Because water is an electrically neutral compound, right? We have hydrogen ions. There's two of them. And they're 2 electrons. Okay, that's a neutral. We have oxygen atoms with their 8 protons. Is it 8? Yeah. And they're 8 electrons. And that's all neutral. So let's have a look here. Some compounds have properties that we call polarity. And this is the cool thing about water. This is what gives it its remarkable structure. Oxygen is a more complex atom, obviously, than hydrogen atoms. Hydrogen atoms are the simplest we've got. It's the most common element in the universe. one proton, one orbiting electron, and pretty much symmetrical as a single atom. Oxygen has electrons in orbit in a couple of different shells, several. And in the outer shells, oxygen is kind of missing a couple of electrons. It's got spaces. It's got room for electrons in its outer shell. It's neutral, but things would be energetically more favorable. Oxygen would be a happier little atom if it had a couple more electrons, if it wasn't for the problem with charge. So oxygen is very reactive. Oxygen works very well with other compounds to form molecules, and oxygen has a tendency to hog the electrons when it's in molecules of that sort. So in a a water molecule, the oxygen atom tends to keep the negatively charged electrons for a greater period of time than those positively charged, or than the hydrogen atoms. And so any given water molecule tends to have an asymmetry of charge. That is, the oxygen atom tends to be a little bit negatively charged all the time, and the hydrogen atoms in the molecule tend to be a little bit positively charged. And so water molecules then have a tendency to attract each other. That attraction between the different elements of a polar molecule, a water molecule that's a little bit negative on one side and a little bit positive on the other, causes molecules to tend to attract each other and actually to organize themselves. And we call that attraction hydrogen bonding, which I think you may have heard about already. Hydrogen bonds are very, very short term. Water's a liquid because it's not, the bonds are not hard and fast as they are in, let's say, a solid metal or plastic or some substance, polymer of sorts. But it's a liquid, and the bonds are made and broken all the time. But as those bonds are made and broken, as the liquid flows, the molecules don't let go all that easily. They stick to each other. They're reluctant. And so instead of spreading out on a piece of wax paper, for example, hydrogen bonds keep our water droplet kind of convex. Because spreading out means separating the molecules more, right? Spreading them all out. In the case of something like mineral oil, or even most of the alcohols, which are slightly polar compounds themselves, they aren't not nearly as viscous because there is less hydrogen bonding, or maybe no hydrogen bonding at all, and they tend to just simply spread out on a film and not hold together. Well, that hydrogen bonding and this tendency for cohesion gives water a very unique structure and a very stable structure. And if something is going to be mixed with water, it had better sure as heck contribute something, because you're disrupting a very structured compound. Liquids we think of as being without structure. There's lots of structure in many liquids, water being one of the most structured of all. So if we're going to put something in water, it's got to be compatible with water. Biological structures, macromolecules, enzymes, organelles, membranes, all those parts of cells would not function at all if they were not compatible in some way with water. And in fact, cells take advantage of the structure of water, both the attraction to water molecules and also a repulsion, a hydrophobicity, a reluctance to mix with water molecules in the case of nonpolar compounds. And that's the principle of membranes. I'm going to give you some examples here in a little bit. Anyway, I want to talk a little bit about some of the advantages of water structure, of cohesion. You may wonder, does anybody know why trees can grow so high? They have to get water from the roots, and they've got to pump it all the way up. You take a garden hose, turn on your outside tap, shoot that water in the air, and try to hose off your roof. You could probably do it if you got a one-story, but I bet you can't do it for a two-story, not unless you really squeeze that jet down. There's a limit to how high you can shoot the water under pressure. There aren't any mechanical pumps in trees that I know about, not a mechanical pump. There certainly aren't. Trees don't grow only over artesian wells where there's enough pressure to just force the water up there. So how do you suppose water gets up into the top of a tree? Capillary action, cohesion, you have cells as units, right? And if the cell on top is a little drier than the cell underneath, then there's a tendency for water to move through the porous membranes and cell walls that separate them simply by the law of mass action. By colliding more on one side of a wall than on the other and going through, then water then moves from one cell to the next, right? And so through capillary action, water can move all the way up to the top of a giant sequoia, or I guess it's the redwoods, I think, that are the tallest trees. They can get about 400 feet. Pretty impressive. The structure of water allows it to dissolve acids, bases, and salts. Water is actually referred to sometimes as the universal solvent, meaning it's capable of dissolving more substances than almost anything else we know. It's not truly a universal solvent, or we wouldn't be able to keep it in anything. It would melt the plastic here, for example. You can't contain an irresistible force in a container, but it's a pretty good solvent. And because it's able to dissolve such a wide variety of compounds, then it facilitates a wide variety of reactions. Reactions that are based on acidic properties of compounds, reactions that are based on basic properties, and so on. Water molecules can bond very readily with other polar molecules. They form actually hydrogen bonding in biological structures. In fact, their interaction with proteins allows proteins to fold, to form helical structures, to produce little pockets that are what we call catalytic sites, where they perform chemical reactions in cells. All the properties, though, are based on, and the structure of the proteins are based on interaction with water. Take water out of the picture and dissolve your proteins in oil or leave them out dry. They don't function anymore. Water is intrinsically involved. And something else that's important that I don't think I mentioned here is that water contributes components to chemical reactions, biochemical reactions. A lot of reactions inside cells involve grabbing hydroxyl groups, OH, or hydrogen atoms, or oxygen compounds, and so on. And water contributes its ions, its own ions, H plus and OH minus, hydrogen ions, oxygen ions. So it's important in a number of ways to what goes on inside cells. And one of the really neat forces and one of the neat properties of water that helps maintain cells is the hydrophobic properties of some compounds. In particular, phospholipids make up the membrane that surrounds the cell, and also the membranes that make up many of the organelles within inside cells that give the cell the shape and so on. The reason that phospholipids consist of a group that is polar, that's charged, that interacts very, very well with water, or can be partly charged, and hydrocarbon chains that don't interact at all with water. They're just series of carbons and hydrogens for the most part, maybe some other, a few exotic elements tossed in there. And they are repelled by water. They interfere with the structure of water, in fact, if you try to mix them. They're the equivalent of mixing oil and water. And so because you have these nice little polar groups that line up and interact with water, and you've got this barrier in between of compounds that don't interact with water, and they're all part of the same molecules, they form very effective wrappers that can surround compartments, surround the whole cell, surround the nucleus, surround the organelles, and so on. And they become very stable when they're hooked to proteins, which in turn rely for their structure on interacting with water. In short, we don't exist without water. We are defined by water. We're the water planet, which is probably why life is here in the first place. And that will do it. Do you have any questions?